Okay, so these notes are to do some of the summarizing that's in the reading that is in the Unit 2 folder for Activity 3, the Presumptive Blood test. You can find that reading, like I said, in the Unit 2 folder down with Activity 3. It gives you sort of a general overview of all the topics that are in your analyzing, but I wanted to do a couple of things via notes so that we could continue our discussion on Monday. The first thing that I want to talk about is the things that you tested. You tested iron 3 chloride, iron 2 chloride, copper 2 nitrate, and rust, which was iron 2 oxide. Iron 3 oxide. These things and how to name them is something we're going to be going over at the end of this activity, but I wanted to talk a little bit about how to figure out the charge on those ions, which was what it asked you to do in the procedure. So if we look at the periodic table, over in the S block, you'll remember that so over in the S block, you were looking at compounds that were more likely to form your +1 and +2 ions because they had a very low ionization energy. They were very willing to give up an electron from their outer shells to get to that stable outer 8 in their outer shell. And so you get things like your +1 and +2 ions. So then over in the P block, remember things like the halogens, chlorine, fluorine, iodine, it's not Fl, it's just F, isn't it? Had very high ionization energy, so it's very hard to get rid of an electron, so they were very willing to take on an electron, and they would form your -1, -2 ions. So if you look at chlorine in this iron 3 chloride here, chlorine is willing to give up that -1, but there are 3 of them, which is what that 3 means here. So in order for 3 chlorines, each with a -1 charge on them, to neutralize when they're bonded with an iron, that iron must have a 3+ charge. So based on that, I'll tell you that this nitrate is what we call a polyatomic ion. Poly meaning many, atomic meaning atoms. So you notice it has nitrogen and 3 oxygens. That nitrate ion is a 1-. So that should tell you how to figure out what the copper is. Oxygen is a 2-, which you should be able to figure out from your periodic table. So you should be able to figure out what the different charges are on these things in your procedure when it asks you what's the charge on this ion. Another subject that I want to talk about is that's not fully covered in the reading is this idea of activation energy. So activation energy and catalysts. Okay, so we know that all substances, if we have a bunch of molecules in a container, those all have kinetic energy. That's the energy stored in moving things. So kinetic energy is energy stored in moving things. Recall, those of you that had the physics class here, that when we get down to the nano level, nano kinetic energy is what we call thermal energy. Okay, it's that energy stored down in the particles that are moving. So in chemical reactions, what we have going on is that these substances that are mixed together are moving. So pretend we have 2 substances here mixed together and they're moving, okay? They're going to go through collisions when they're mixed together. And during those collisions, thermal energy is transferred. If enough thermal energy is transferred, then bonds, they bend, they break, and they stretch. So those bonds, those things holding those particles, those molecules together, for example, in H2O, there are bonds between the hydrogen and the oxygen. If the collisions have enough, if enough thermal energy is transferred, enough kinetic energy is transferred, then we get a chemical reaction, a rearranging of particles. And I'm just going to abbreviate reaction here. Chemical reaction is a rearranging of particles. So that rearrangement happens if there's enough thermal energy transferred when bonds or when molecules hit, when they collide. So some molecules within a substance are moving fast enough to cause that bending, breaking, or stretching, but some do not. And so basically what we've got going on is that the chemical reaction happens at a certain rate based on how many of those molecules have enough energy. Kind of think of it like this. Let's say you have a ball. That ball is rolling along the ground and it comes to a hill. If the ball has enough kinetic energy, then it'll make it over the hill because that kinetic energy will transfer. For those of you that have had the bar charts before, if we look at the ball and the earth as our system, kinetic energy, gravitational potential energy. If the ball has enough kinetic energy at position A, then it will get to the top of the hill and roll over. Okay? If it has enough to roll up and over the hill. The same thing with reactions. If there's enough kinetic energy stored in those particles, then we will overcome the hill, which in this case is a chemical potential energy. Okay? So in a chemical reaction, we show that by showing the progress of the reaction, which you can kind of think of like time, and we show energy over here. So we graph the energy of the reactants down here, and then we show that there's this amount of energy that we have to overcome in order to get to the products. And we'll talk more about this when we get to our alternative energies unit, but when the reactants are higher than the products, we have an exothermic reaction. Energy is released. But this amount of energy that it takes to get up this hill, okay, this is called the activation energy. And in the reactants, if there are enough of those particles that have the right amount of energy, the reaction will progress and we'll get products. But if there aren't enough, it'll go very slowly. Only every once in a while will we get the reaction to happen. This is what's happening inside your luminol reaction. So when we added the water to the luminol, there was some other stuff in with the luminol, but the luminol powder, we get the H2O2, which is hydrogen peroxide, reacts with luminol to make light, water, and oxygen. Okay? And so if there's enough energy, this is what's going on inside your spray bottle, we'll get light. However, that reaction is very slow. There's very rarely enough energy over here in the products or the reactants to get up over that activation energy. So what we do is we add a catalyst. A catalyst is a substance that provides an alternate route with a lower activation energy. So you may have heard it said that the catalyst lowers the activation energy. Well, that's not exactly true, but it does provide an alternate route. So an example would be, like, let's say that a bunch of people are going to climb a mountain, okay? And only some of them can make it up and over the mountain. However, someone comes along and they dig a tunnel. Someone comes along and digs a tunnel through the mountain, okay? So that tunnel has takes lower energy to get through. So it's not that we've actually lowered the mountain, we've just created an alternate route. The tunnel is like the catalyst. It's created an alternate route with a lower activation energy. So blood, or something in the blood, actually the hemoglobin, which is a protein in blood, is a catalyst for the luminol reaction. Okay, and so essentially what we end up with is a new energy graph So if this is the original luminol, just luminol and hydrogen peroxide, we end up with light. Over here, the, oops, new color here. When we add the blood, and I use red because it's kind of like blood, we have our reactants, the energy is now lower. The activation energy is now lower because the blood has catalyzed that reaction. Now the blood itself does not get used up in the reaction. It doesn't actually react with the hemoglobin. It just acts as a catalyst. And catalysts, these substances, there are several ways that they sort of create alternate pathways with lower activation energy. One way they do that, they might do that by putting a charge on one reacting molecule to make it more attractive to the other reactant. Okay, that's one way. They might alter the shape of the reactant to make it react better. So I'm not exactly sure what blood does to the luminol reaction, but somehow it catalyzes the luminol reaction. So that's just some information I wanted to give you on what a catalyst is, what it does, and how it works. The rest of the information you need for the analysis is in the reading, so you can do that, and then we will discuss the analysis on Monday.